Okay guys, let's take a look at today's lesson. We're going to be looking at limits, both graphic and numeric. So let's take a look. This first portion up here, this definition of a limit, this is basically pretty complex, the definition of a limit. We really aren't going to be looking at definition of a limit like that in here. We're going to save that for multivariable. It is complicated and pretty difficult, and it's not on the AP test, so it uses sigma and delta and some other things, so we're not going to look at that. We're really going to look at a more informal definition of a limit, and that's where this portion comes in, the relationship between one-sided limits and two-sided limits. So here, I'm sure we were all familiar with or had this in pre-cal, the limit as x approaches a of f of x equals L, so some number, value, if and only if. Okay, that's not a typo. IFF means if and only if. If and only if the limit as x approaches a from the left, remember those from last year, the little negative, equals to that number, whatever that number is, which is also equal to the limit as x approaches a from the right. A little plus up there. So that's what we're going to be looking at, is basically our full limit does not exist unless the left and the right-handed limit equal the exact same number. And that's how we're going to look at, we're going to define the limits for us today. So let's look at this particular limit. We're going to look at it graphically and numerically. As we look at the graph of it, here's the graph of this particular function. Notice that there's a hole right here. We are approaching 9, an x value of 9. So we are approaching this x value basically from the left and from the right. Notice that we are approaching the same y value. Okay, we're approaching this y value of a 6. Now, we don't actually get to ever be 6, and I'm just going to tell you the limit is very upset that it can't be 6, but it's really trying very hard. But it doesn't get to be 6. But it actually does equal 6. Okay, that is something that really trips students up, this little hole right there, especially if I were to add a function value there. If I add a function value here, many students would just be confused as to what to do. So let's talk about that scenario. If I have a function value here, that's like off the beaten path. All right, I have to stay on the road or the function in order to look at a limit. And so as I'm going left and right, my limit value would be a 6, but my function value would be, wherever I put that, maybe 3.5 or something. So just know those are two different things sometimes. Sometimes the limit value does not equal the function value. Okay, and we'll be looking at that in more detail. That just means it's not continuous. So that's basically graphically, the answer to this limit is a 6. Let's look at it numerically. And you may remember doing tables last year, numeric tables for limits. If we of course we need a calculator. No one's going to expect you to do this in your head. So we would look at patterns. So mathematicians look for patterns. And when we're doing numeric limits, we look for a pattern. As we approach 9 from the left, 8.9, 8.99, so getting closer and closer to 9 from the left, notice that my y values are getting closer and closer to 6. Okay? And then we look over here and we approach 9 from the right. Again, we're looking for a pattern. So 9.1, 9.01, getting closer and closer to 9 from the right. Notice that my y values are getting closer and closer to 6. So with this information, this numeric information, I could also say that the limit equals 6. So that's just the two things we're going to be looking at today are graphic and numeric. Any questions so far? We doing okay? Okay, we have a few examples. So let's go to the next slide. Okay. So this one, the very first example is graphing. We're going to look at a graph. Now, if the limit doesn't exist, your pre-cal teacher may not have had you do this, but I need you to do this. I need you to show me why. All right, in other words, I need you to show me the two-sided limits, from the left and from the right. So let's look at our function. It's called h of x. That's what this is a graph of. As x approaches 0, we can look and see that we are not approaching the same value from the left and the right, so that limit does not exist. Okay, it's not acceptable to just write D and E up there. We have to show me why. I need to know that you know why. So what we would do is we would say the limit as x approaches 0 from the right of h of x. Okay, so let's look at it. We are approaching 0 from the right, we're headed from the right, and our y value that we're approaching is a 2. Okay, and then the limit as as x approaches 0 from the left of h of x. Okay, so let's see what's going on here. We're going on here, and then we get on a crazy roller coaster ride. Okay, that's crazy right there. That's called oscillating behavior. And when we have oscillating behavior, that is actually officially D and E. That does not exist. So, therefore, these three little dots that look in a form of a triangle, that's mathematics, a mathematic notation for therefore. Therefore, the limit as x approaches 0 of h of x is D and E. Okay, so that's what I need to see if the limit does not exist. I need to look you to show me from the right and the left what the values are to prove to me why it does not exist. Okay? Am I going too fast? We okay? Alright, let's take a look at the next one. We are headed towards an x value of 2. Now we visually look at this and we see, well, goodness gracious, we're not approaching the same number from the left and the right, so that one doesn't exist. So we need to go through our proof. So the limit as x approaches 2 from the right of h of x. So let's see what's going on. 2 from the right. Looks like we're approaching the number 1. The limit as x approaches 2 from the left of h of x. Okay, so we're coming from the left. Looks like we are approaching a 3. Therefore, the full limit does not exist. The limit as x approaches 0 of h of x equals D in E. Okay, we getting the hang of that? We okay? Alright, this the last one on this graph, we want the limit as x approaches 4 of h of x. Okay, so here we're approaching 4. And actually, we're approaching it from the left and the right. Our x value from the left and the right is all headed towards a y value of 2. Now, I know it's a little disturbing. There's a hole there, but it's okay. Do we have a function value at 4? We don't, do we? There is no function value at 4. A lot of times, they might put a function value in there, just, put a point there. Maybe they might put one there, but we don't have one there at all. There actually is not a function value at 4. Okay. Alright, so let's take a look at this limit. This one, you may have even done this one in pre-cal. This one, but graphically, if you put this in your calculator and you zoom in at an x of 0, it gets even, the more you zoom in, the crazier it looks. I mean, it's just crazy. Crazy oscillating behavior. So this one is, this one does not exist because of oscillating behavior. And if you look at the numeric, they have done this one numerically. If you look at the numeric portion, you'll see as we get closer and closer to 0 from the left, the y value bounces around. And we get as closer and closer to 0 from the right, the y value is still bouncing around. So that shows you numerically that it doesn't exist. Now in our calculators, some of our calculators really probably wouldn't even pick up this nuance. I don't know. Some of them just would say 0, 0, 0. But the reality is it is flipping back and forth. It's going crazy. Alright, our last example for today. We're going to do this one graphically. So here's our limit statement. That's what the graph of this looks like. And we can see from the graph, this is called a jump discontinuity. So it doesn't come together. So this one is a D and E. So if it's a D and E, then we need to show both sides. So we say the limit as x approaches 0 from the right of x over absolute value of x. So as we approach from the right, we hit 1. The limit as x approaches 0 from the left. As we're approaching from the left, we hit -1. Therefore, the limit as x approaches 0 of x over absolute value of x is D in E. Now, if you like to conserve energy and you really don't want to write, now that's a fairly small function to write. That didn't take me that long, but what if it was gigantic? You could assign so we could say f of x equals x over absolute value of x. We could say that, and then every time I write the limit I could use f of x instead of writing the function again. Just so that you know that's acceptable on the AP test, that's acceptable to me. I want you to know that that is okay. If it's really gigantic, you might want to do that. You might want to label it and then use that label every time instead of writing the function over and over again. Alright? How are we doing? Everybody okay? Alrighty.